PI side to make sure that you can beef up their numbers of success, which in turn, I guess, makes you successful. So not always a bad thing. So yeah, I spent 3 years in Johnstown there and doing antenna testing, kind of DIY antenna testing. I didn't have access to a large amount of resources. There's some resources there, but yeah, I guess now that I've moved on, so basically, yeah, I kind of got bored with it a little bit in Johnstown, New York. When I joined, they said they were going to grow the antenna division, and then you get there for a couple of years, and you realize people are just telling you that to get you to stay there, and things like that. And you don't really see the pieces being put together. So I kind of just applied. First, I wanted to stay kind of local to New York, just because I was a kind of New York kid. I was born and raised in Brooklyn, and from New York City, and then spent basically 7 years or 6 or 7 years in upstate New York. So I was like in upstate New York, but yeah, there wasn't a whole lot of antenna. There's not a whole lot of like manufacturing. There's a lot of like wafer and stuff like that for if you wanted to get more into that. And like microchip manufacturing, silicon wafers, these kinds of things in the upstate New York region. But I guess I just didn't see a lot of antenna companies. San Diego has kind of a background in antenna companies. Qualcomm was there, founded there, and they basically invented the smartphone. I guess they invented CDMA and had all the patents for that. But yeah, I kind of relied on that once I moved to. So once I moved to Tau Glass in San Diego, kind of appreciated more all the features they have there, coming from kind of a DIY electronic antenna testing. Anyway, I'm probably spending too much time on this slide. I have more slides that kind of goes through the. All right, cool. Yeah, so let's talk about everyone's favorite school. It's my favorite school anyway. I guess I think some people's favorite school. SUNY Oneonta. Yeah, so I think the physics department right there is great. Really accessible, and then it's great to be able to go and talk about physics kind of at any time. You don't have people brushing you off. And yeah, I was in the 3-2 program with the engineering focus, and did the all the intro to engineering classes. Particularly with this amazing internship program that he was running there. Yeah, the CDAR projects and going to CIDR, or I guess I have that. It's CIDR, right? And CDAR was the conference.
That's right. Yes.
Geez, man, what a rookie mistake. Yeah, CDAR was the conference. I remember what coupling energetics and dynamics of atmospheric regions. So I remember the abbreviation wrong, initialism, I guess. Cool. Yeah, we had this awesome. Basically, I think in my first year freshman at Oneonta, I was taking summer school. The 3-2 program is quite a bit of credits. You're taking 18 credits a semester. Sometimes it's helpful to do at least maybe one summer of summer school classes, so you're not pulling your hair out. Take a little pressure off of the credit load there. So then basically after that, I was like, hey, Hugh, I don't want to do that again this summer. And he said, you're gonna have to get better grades than that, Tim Kelley, if you want to get into my internship program. So that was it. Yeah, Hugh challenged me there, and I got better grades, and I got into the internship program. So yeah, he had me clean up my act. Yeah, so in 2009, I was in Oneonta working there over the summer, and that was good times. And then after that, in the summer of 2010, we got into, I guess we were doing a joint research with the applied research labs at the University of Texas at Austin. I think we were both on the same grant there. So it's almost like a feeder program where we'd have people get their sea legs, I guess, in Oneonta in the first summer, and then go to UT Austin the second summer. I think Peter Anderson followed the same kind of internship program a year before me. And yeah, as a direct result of these two internships I had through the Oneonta physics department, I was accepted to the MIT Haystack internship, I guess in my first year at RPI in 2011. So that was great. Yeah, there's me and Anthony DiPietro ages ago presenting our poster, and then here's the whole cider gang. See if I can remember. I think I got everyone. Yeah, it's Trevor, right? And Michael and Scott and Paul and Peter and me and James and you. There you go. Yeah, and then this is actually me right here at the MIT Haystack Observatory. You can barely see me, but I'm in the photo. So then, oh, is this gonna let me? Oh, here we are, RPI. There I am, yeah, Bruin crew. I guess that was kind of like, the highlight of me being at RPI. I mean, the EE department wasn't great. I don't know if I can speak for the other engineering departments at RPI. It seemed like it was kind of shot in the dark about whether you get a good professor or, absent, or I guess a ghost professor. Yeah, it was kind of, sink or swim, and then it was, I don't know. To me, I wasn't a huge fan of like I guess I just figured as I'm paying money to a school that I would want to be taught by the people at that school. And to me, it just didn't seem like, oh, me learning out of a book in the library. I mean, I could stay home and learn off YouTube, something, right? Yeah, so RPI is super well known on the East Coast, and yeah, I've actually think I've gotten out of my buddy got out of a speeding ticket because I was in the passenger seat and went to RPI. But I would say that in the West Coast, I haven't met a lot of people that know what RPI is, or I've said maybe in engineering circles, but doesn't really have the same, I guess, name drop. This is kind of an FYI in terms of West Coast, how folks are out here. I mean, they have all those fancy UC Berkeley and whatever, and all those West Coast engineering schools that they're very proud of out here. So just thought I'd share that because I guess I always everyone seems to know it on the East Coast, and was a little surprised, I guess, on the West Coast when nobody seemed to give. It was, well, on the West Coast, it's what have you done for me lately? Nobody really cares where you went to school. Electrometrics was a good time, though. I will say that. It's very. Johnstown's a pretty small town. I guess I've heard it described as what Oneonta is to Albany, Johnstown is to Oneonta in terms of size. Yeah, it's a pretty small town. I was riding my bicycle to work here and riding through the industrial park there. And yeah, that is the outdoor antenna test range there. You see this tent here. So basically, anytime I wanted to test any antenna prototype I had, I would have to bring this 80-pound positioner outside. I'd have to wheel the VNA outside, and then set up just two antennas, point them at each other, kind of look at the S21, the forward transferred power, and kind of just swap in, take a reference antenna and then swap in my antenna, and then we do like an XY cut to look at the pattern, and then also look at the just kind of forward gain. We're mostly getting a sense of how omni the antenna was. We did do some stuff like millimeter wave, so believe it or not, we had a hill behind the antenna test range. You could always see this hill in the measurements, so you're pointing two antennas at each other and you blast the signal this way. You get reflection off the hill. So I was able to implement basically a filter, time domain reflectometry filter, where I knew the amount of time that it would take to get the signal between the transmit and the receive antenna, and I knew that anything arriving at the receive antenna after that time was a reflection, particularly this big hill behind there. And then so by creating a gate, which is kind of a common function that a lot of VNAs have, they use it for like fault analysis and things like that. I was able to filter out the effects of that hill. And then we got like smoother antenna patterns as a result. So that was kind of interesting. And that was just kind of, no one like asked me to do that. I kind of just was staring at the hill every day and getting pissed off why it was in my measurements all the time. So where there's a will, there's a way. But yeah, it was a whole like 4-hour affair to get this set up. So I like have an antenna prototype I wanted to test, maybe after lunch. And the rest of the day is spent, setting it up, breaking it down, doing some measurements. Then you come in the next day, work through the data and stuff. Quite a bit of work there to do one antenna test. Talking about like a 4-hour test time. Yeah. Yeah, I also worked with the Protomet LPKF. I kind of cut my teeth on here. Yeah, it was good. It reminded me kind of Oneonta a little bit, where they sit you in front of a machine and say, hey, this doesn't work and you need to make it work. Here's the manual. Yeah, kind of reminded me of the rectilinear plant there. We had did was an independent study, I think, with Mahanta back in the day. Yeah, so that was kind of fun. Yeah, just sorting through, and the machine had been collecting dust for years. Nobody could get it to work. And yeah, I mean, you left with a large amount of time to kind of mess with stuff all day. Slam your head against the wall long enough and you're able to make some progress. So yeah, we were able to get it running and making some antenna prototypes. Yeah, that's just kind of what I would make. Can you guys both see my screen and my face? Or I don't know.
Yep. Yeah.
All right, yeah. Jeez. Can you guys see this? Or, I'm not sure where the camera is.
Yeah. Yes.
All right, cool. Like basically we had an old board or something. They didn't have the design files for it, but they had a recent order for more boards. And this was going into, yeah, like a EMC, kind of like injecting AC voltage onto DC line, some sort of sensitivity here. So there's all these traces here. And basically I think they had maybe the DXF, and I needed to just remake the exact PCB layout that they had. So I kind of traced over everything and made that there. Another design we made there was this kind of it's like an approximation of a bicone. So you just took two PCBs and slotted them together.
You got to hold it up a little bit higher, Tim. Perfect.
Oh, yeah. So it's two PCBs that get slotted together. There's an SMA connector comes off the back. And yeah, basically this is like kind of an approximation of biconical antenna element, where instead of having to machine an actual cone, which is a bit more costly, we were seeing whether we could just slot two PCBs together, stitch together the vias, and kind of approximate a cone in this fashion, have maybe a cheaper, less machine oriented. What ended up happening is that there's antenna pattern nulls here, and here, which I guess would make sense. There's no copper there to radiate, and as you go from that transition region, I think we were doing some higher frequency stuff with this, so it ended up not working, which is why I still have it. But it's still a fun prototype to make, and half of engineering is figuring out what doesn't work. So tile glass. Yeah, so basically I've been working there for 3 years. I randomly got a phone interview with Tile Glass 6 years ago. Yeah, they basically hired me off a phone interview and said, hey, do you want to we'll pay for you to move to San Diego. And I think I checked the weather report. It was around March or something. It was we're gearing up for second winter in Johnstown, New York. So I think it was, we were predicted to snow, and it was like 80 degrees in San Diego. So packed up my bags and said, hell yes, I want to move to San Diego. San Diego's a nice town. There's a lot of communications and biotech industry background. So Qualcomm was founded here. They built the Chargers Stadium. It used to be Qualcomm Stadium, so they built the Chargers Stadium here, and then the Chargers abandoned us. And there's also a big biotech. So Scripps is out here. UCSD is kind of a big biotech school, and Illumina is another big biotech firm. There's a couple big biotech research things here, and also there's like all the offshoots of Qualcomm. So there's a lot of people that they work at Qualcomm for a couple years, and then they maybe spin off and start their own company, but they're still in San Diego. They've already gotten used to the San Diego life and things of that nature. So there is a lot of like, it's not just, oh, there's Qualcomm and like the big Microsoft. I think Microsoft and Apple both have opened offices recently. But I think a lot of what's nice about San Diego is you have a lot of that talent that stays local, after they leave some of these big companies, and maybe they take some good ideas, they develop some wacky product or something, and and then they come to us when they need antennas. So yeah, the design center in San Diego is pretty awesome. We have a passive and active Howland 3100 1-meter chamber. I have some photos here. So that's, it goes all the way from 700 mega to 6 gigahertz and kind of tests all the protocols under the sun, LTE, all that's good stuff. And then we also have a larger 3-meter chamber from 600 megahertz to 8 gigahertz. Pictured here, we have our Halloween celebration. Actually, I like this photo because my project manager dressed up like me for Halloween. It's a wig, believe it or not. He was pretty specific. He had to get the right wig.
Hey, which one's you? That's amazing.
Just had to have the wig, match the mane here. So that was a good, that was a good time. We have some fun here. It was just 80 the other day, and we went for a engineering lunch, which evolved into an engineering brewery tour. So it's always fun to take the afternoon and enjoy some of the good weather here in October. We have the fancier version of the LPKF S63. So it was funny enough that I, acquired all these LPKF skills or troubleshooting skills, and then it actually had a broken LPKF in their Ireland office when I first joined, and then I was able to fix their LPKF here as well. But then I actually asked them. It actually took me 5 years to get the 64 copper cutter because my boss thought it was a waste of time to spend, because essentially the engineer has to spend a decent amount of time troubleshooting the thing. They sell it to you as you can just plug in your PCB design and walk away, but then you come back and there's some error, it needs the user to change some settings, or there's definitely a little more babysitting than one would want. A lot of what I do use is CST, which stands for Computer Simulation Technology, which sounds like a fake software, but it's actually one of the premier electromagnetic simulation softwares, along with HFSS. Basically, you're either in the HFSS camp or you're in the CST camp. And we've been using CST since I've been here, so I probably have a couple thousand hours on it, and I have the dubious honor of being the CST expert when we have junior engineers asking for questions on why is the simulation not matching my measurement. It's because your simulation is wrong. The simulation should always match the measurement. Otherwise, what would be the point of paying for simulation software? For PCB layout, we have Altium, which is pretty industry standard. I know some folks use like pads or other packages, Cadence. Altium's kind of our go-to there, and actually works out pretty well. I think I have some talk about design cycle stuff on these slides here, if I'm not mistaken. We can get into that in a second, but and then we also have the Silhouette Studio copper cutter, which is actually not, it's pretty, like some of these are obviously have big price tags, Altium, CST, LPKF. This is $100, the Silhouette Studio. And you can actually prototype FPCB antennas on it. So yeah, it's a little secret sauce tip for you, that you can buy a Silhouette. It's typically for like wedding invites. and like stickers and things like that. But if you take a piece of copper tape, big sheet of copper tape, and then you just stick it to the same thing that you would put the stickers on, you can have it cut out any, DXF pattern that you could dream up. So you can take and then just, solder down a coax to the ground and the feed, and there you go. That's your antenna. So might be worth looking into for the Oneonta lab, or yeah, happy to support that. Just like a kind of a quick thing, and then it's like free software, and it's like $100 copper cutter. So might be helpful for doing some kind of how many antenna designs you do in the lab there. But oh, how do I? Oh, here we go. Chambers, yes, my fun. My life. So these are the Anechoic Chamber. So the cone has been selected to create a quiet zone in the region under test. Typically, it's like a 12 by 12 cube where you're not having reflections. You can put an antenna in there. I kind of liken it to like if you wanted to go into a recording studio and you only wanted to hear the sound of your guitar, and you didn't want even reflection off the wall, the reverb to kind of spoil your recording. In the same manner, if I wanted to test an antenna, I wanted to only look at the antenna. I didn't want to look at reflections. I didn't want to look at, as we see here, I didn't want to look at the hill behind the antenna, have that included in my measurement. And I don't want to design a filter and a filter process for each measurement. I just spend like most problems, you just throw money at it. And yeah, you have this. I mean, this is this is probably a 1.5 million chamber for this one. This one we got on the cheap, the 3-meter one, because sometimes you can do that. There's like a clearance. Some lab is shutting down, and they just, whoever has real estate to take that chamber will take that chamber at a lot less than they paid for it. Kind of a buyer's market thing where, let's say, some startup or something ran out of funding, and they've spent a lot of money in their beginning rounds to buy a chamber, and then basically they need to get rid of it, right? They're just liquidating everything. So you get this one on, wait for a fire sale on chambers, and then you can pick up some good stuff. But yeah, this creates that quiet zone that I was talking about, and as a result of that, you can measure the antenna by itself, not and only get get a full 3D pattern. So this is a conical cut chamber. So you're taking sections of this turntable spins 360 degrees like this, and then there's actually a arm that comes down, and so you're taking like sections of a cone and then doing that, kind of volume integral over the whole sphere. And it actually, I know what you're wondering. You say, oh, this is a turntable here. You have an arm coming down here. But Tim, how does it measure underneath the turntable? Because clearly we would be missing the 180 degrees spot. And I would say, hey, that's a good question. We don't. We interpolate from plus or minus around that. I think it only goes down to about 165 degrees on one arm, and then 360 the other way around. So we basically, that 180 degrees is interpolated from the plus and minus 15 degrees around that 180. I say 15 degrees because that's a CTIA test standard for cellular devices. So typically, like our business model revolves around people getting through certification. So Verizon and AT&T have certain limits for antenna performance. This is specifically in the US. Actually, in Europe, it's kind of just let you on the network as long as your peak gain isn't super high or you're not blasting radiation. But yeah, you can get away with a 20% or something efficient antenna in Europe and Asia markets. In the US, they're pretty strict. About having had to be 32% efficient in the lower frequencies, 700 to 960, and then from 1700 to 2700 has to be 50, or I guess 2155 has to be 50%. So that correlates. They have these metrics, TRP, total radiated power, which is just turning your radio on, and at max transmit power, and then seeing what kind of, basically it's just the power minus the antenna efficiency. So it's pretty straightforward. And then they also have the total isotropic sensitivity, TIS test. That is like a receive, basically it's like the difference, how well your antenna can talk and how well it can listen. And the listen part is where we usually run into issues, because it's not simply an antenna problem. It, the noise from the PCB can create, a certain noise level that you're never going to be able, even with the nicest antenna, you're never going to be able to hear below that level. Because it's just, it's like, you're walking down the street and you're freaking bunch of people are talking. Doesn't matter how loud you talk, you're not going to be able to talk above them. I think that metaphor breaks down at some point, but more or less, that's kind of what the VIG is there. So yeah, we do a lot of stuff where we have to explain to customers, saying, hey, the antenna's great. It's just picking up all the noise from your PCB. The antenna's more efficient, so it picks up more noise, which is always seems to be a bit of a problem. Well, people don't like to admit that there's any issue with their device. So yeah, I have a little bit about design philosophy. I don't know how I'm doing on time, but
You're good.
Cool. So this is kind of what I do all day for developing standard products. So typically I'm, in simulation land, and I'll start off with a simulation, and then I will, very early on build a prototype to correlate that simulation. So the idea being that that I could make that simulation model correlated, and I can basically try new ideas in simulation that may be difficult to prototype. So I can, let's say here's a simulation model of, a conical antenna I designed. Let's say I wanted to try some weird pattern somewhere in it, or I wanted to draw a fractal or something and subtract it from the copper, or something odd or something weird here. I could do all those things and then look at, what the effect is in simulation, and I would have faith in the simulation model, since I started with like a baseline model that had been correlated to measurement. So typically, this is a bit of an iterative thing, and so I try a new idea, whether does it improve performance, if it does, then I create like a new model with some feature that does improve performance. And then typically I have performance goals. Oh, it has to have this sort of efficiency. Typically efficiency is the metric, because most of these antennas are going to be omnidirectional, unless you have a specific application where you're designing an antenna for other properties. You're typically just trying to maximize efficiency to pass those carrier certification requirements that I mentioned earlier. But also, you don't want to, when you're developing a standard product, you don't want to, create this big antenna that works great, but only works on the evaluation board, or it's not marketable. So this ends up being a lot of back and forth, where I'm always trying to push for performance, because once you integrate the antenna with all the various plastics, and people are going to put the metal right near the antenna, they're going to put batteries and stuff near the antenna, and then come back to you and say, hey, I put a battery right on top of your antenna and it didn't work, and your antenna sucks, stuff like that. So typically I like to have a little bit of margin in the performance to make my life easier later on. Otherwise, everything would have to be customized. We want it to be plug and play. Then here we have, this is kind of, I like these interesting plots of simulated versus measured data. Obviously simulation tends to overestimate the radiation efficiency a little bit. So when I'm taking simulated data, I'll probably subtract a dB just to bring that a little bit more in line with reality. But still, this is within a dB. This is a wideband antenna that I designed. I believe it's even this antenna, yeah, the BCS 66. And yeah, we can see that we get pretty good correlation there. We're within a dB or so across the whole 600 to 6 gig spectrum. Yeah, we're confident there, and works out pretty well to try different ideas. So why does all this stuff about, freaking antennas, efficiencies, quiet zones, chambers, how does it matter to me, the consumer? So I had been working with Talglass products for several years and integrating their existing product line into various customer devices. And it was kind of an interesting experience where you start to see kind of patterns on what the existing products are, what the typical integration it is from working with customers and, doing, tens and after you've done a couple dozen of these projects, you kind of sit there and well, I kind of wish I had an antenna that did this or was a little bit smaller in this dimension and would just make my life a lot easier. I could, just put the antenna on there and be good to go. So I developed the FXUB64. It's called the Cyclone. I named it after my favorite Disco Biscuit song. And somehow that made it through marketing, but I didn't tell them it was named after a song until after it had been released and all the marketing stuff had been published. So it would be very, I guess, work intensive to change the name now that we have a brand. So that's fun. Yeah, it's always good to put your own spin on things. It's a little cyclone joke there. So yeah, this patent actually had just been granted August 2021. So I filed this 3 years ago. Just got granted. It's anybody can file a patent, but being granted is yeah, it means it's actually original or has some merit, and that nobody in the they're doing cross-reference against the current literature and things like that. Nobody had done it, so I was excited about that. Original ideas, I guess, don't happen every day. And then I worked on a project where I integrated this antenna into these payment terminals. So in New York City, they have these payment terminals where you can tap your phone, and it has, tap to pay system. And they needed LTE to, verify, basically turn this into a cell phone so that they can verify everyone's payment details, go back to the wireless backhaul back to the financial institutions and stuff. So yeah, kind of a bizarre thing where my antenna, I was born and raised in Brooklyn, and I've even gotten, tickets or whatever for jumping the turnstile. But now I'm improving turnstile security. And so, yeah, putting my antenna just on there, and it's in almost every single. I was just in New York City visiting my parents this summer, and I saw one of these. I took a picture. Yeah, it's pretty interesting. Yeah, that it's been deployed there, and yeah, that's me, the kid from Brooklyn, giving back to Brooklyn with antennas, I guess, or I guess engineering the technopocalypse, depending on your camp there. Because yeah, some of these applications do, and this one I guess is all right. I don't know if you guys like it, but some of them do come off as a bit gimmicky. And then I guess I have a larger antenna design example here, and we can just go over quickly. Oh, and this anti-static bag. Can you guys see this all right? Or...
Yeah, I think half of it.
Yeah, I think what I got to do.
Move to your right a little. Perfect.
Yeah, there you go. So this is a 2x2 antenna array. The idea is that I can use all four antennas and phase them correctly, offset the phase to create a directional beam, and I can kind of steer the beam. So this is directional this way, And I can essentially, by changing the relative phase on these four elements, I can kind of move it backwards and forwards to kind of do position finding. And we developed this for RFID tag reading. So the idea was that this would go on like the ceiling of a clothing store, and that there'd be an RFID tag in every piece of clothes, and then it would read the tag. And then the idea is that this would has both horizontal and vertical polarization. So you can, if the tag is one way and you're not getting a read, you can switch to the other polarization and see if you get a read to see if the tag is this way or that way. And I guess there's been some studies that people buy more clothes when the rack is fully when the rack is full, I guess, or there's more clothes on the rack or something, or people don't like empty racks in clothing stores. But this was all an idea pre-COVID. I don't know how much of that industry has maintained since then, but yeah, then the fun part is that I had like complete design control there, where their PCB would plug into our PCB, and then we have a digitally controlled network here. So this is a switch that switches between vertical and horizontal polarization, and then so this is digitally controlled. They're able to put their ones and zeros here, and then they also have 4 RF connectors for output here. So they control where the beam through this connector, and then they offset the phases through here for each feed for their feed network. So yeah, it's kind of cool. And then all these mounting holes, it gets mounted on the plastics of their enclosure. So it's kind of an interesting application where I was doing kind of the PCB layout and the design here, and then also doing the antenna design there, and also integrating their 3D step files to verify that there was not going to be any issue interfering. I actually had to cut the corners of the antenna to compensate for the draft angle of their enclosure. They didn't want to change anything on their enclosure. Yeah, then I had to retune the antennas for that. And then this is a partial air gap design. So it's FR4 based, but then I used to get some additional efficiency. I did some air gap there, and we have plastic spacers that maintain the antenna height. Yeah, this was a fun project, and kind of a lot of different skills that I had been developing all like kind of came to fruition, like the PCB layout and then importing the entire assembly into like a final simulation check there. And yeah, turns out green solder mask is more accurate than black solder mask. So there's a fun fact for you. Cool. Yeah, so I hope that was helpful, or I don't know if it was inspirational, but I hope so. Anyway, I guess I wanted to just kind of share that career path and stuff. So if you guys were looking to follow a similar path, you can kind of have some of these milestones. I would say to avoid this milestone of doing poorly at your second college, but you can skip 2 and go straight to 3 at a fancy. But it is a good I think it's a good tidbit that, hey, like it didn't matter that I had an internship at MIT. It didn't matter that I had 2 bachelor degrees. They just saw the 2.5 and they're like, take a freaking hike, bud. But yeah, no, it's
On the other hand, a potential lesson in that too is that once you get that first job, that 2.5 doesn't seem to matter.
Right. Yeah. Yeah. It's just good to keep that in mind. It always seems like colossally important when you're in school. But yeah, it's good to know that yeah. Not that I'm telling you to slack off in any of Hugh's classes or anything, but yeah, it is good to keep it. It's not as it's not going to destroy your life. I mean, and yeah, if I hadn't done poorly at RPI, then I wouldn't have ended up at Electrometrics, and I wouldn't have ended up in Tower Glass, et cetera, et cetera. So,
Before I open it up for questions from the floor, How did you end up at Electrometrics again? Did that come through RPI or?
Yeah. So they had a system where they, I think my boss had gone to RPI, and they have like a whole matchmaking almost system where it's like alumni post job openings, and then that almost like an Indeed.com kind of thing, right? But it's like, for RPI alumni or whatever. So I guess notable alumni can post job openings to that, and then they can get, and then upcoming graduating students can apply to those jobs.
So while you may not have got your first choice, you did have actually a good starting place.
Oh yeah, for sure. Yeah. I think their career resources are great, and they're not gonna like let you, be hurting for a job there. Just goes to show that even the B- to C+ of RPI still gets a job. And then, once you cut your teeth and stuff, nobody really cares what you did in school. They just what you can do for me now.
Okay, so we have a question in the chat, and this is from someone who's gone from Oneonta to RPI. So, Mohammed, are you there?
Hello, can you guys hear me?
Yes, welcome back. Hi, Mohammed.
I'm in a little hurry because I actually have an interview with IBM in a couple minutes, but Tim, I fully agree with you. So the whole Oneonta to RPI like transition, oh my god, it's so rough. It's a little rough, but definitely doable. Definitely doable. And I was gonna ask you how you got your first job out of RPI, but like Dr. Gallagher already asked, and really nice to see you, Dr. Fox, all the students there. 128. Oh, actually, I gotta show you something, Dr. Fox.
What is it?
Can you guys see me?
Yeah.
Oh yeah, now we can see you. Yeah.
I had a program that I was working for Google, and Dr. Fox got me interested in PCBs. So this is my first ever PCB that I made myself. I actually used KiCad, but I'm working on a motor controller right now, and I'm using, what was the software you were talking about, Tim, for one of your projects? It was
Altium. Yeah.
Can you go back a little bit on your slides?
Oh sure. Yeah. Altium. Yeah.
That one. Yeah, Altium. I'm using SolidWorks PCB, and I think it's like based off of Altium. So I'm like kind of using it. So
yeah, SolidWorks.
Into PCBs. PCBs are super cool. They're a lot of fun.
Yeah, they are a lot of fun. Yeah.
You should go talk to Dr. Fox for that. Actually, he'll get you into it.
All right.
That's really great, Mohammed. I'm glad you're doing that.
Thank you. All right, I just wanted to say hi to everyone. Miss everyone.
Okay.
A lot. It's a good time. Have fun while you go your second school. I gotta go.
Good luck, Mohammed. Good luck.
Thank you.
Luck. I'm going to connect you to Tim via email, okay?
Okay, I'll email you. Thank you.
All right.
Bye.
And so, despite your expressed concerns about RPI, seconded by Mohammed, you both seem to have done pretty well.
It's true. Yeah. We're all just pissing and moaning, I guess.
I think electrical engineering is, I think it's a more challenging discipline than some of the others.
Yeah.
Is that fair?
I would say so. Yeah. I knew I had some classmates that were like industrial engineering, which I don't know if that's like it's a real thing, or I don't know. It's not like
We used to call it imaginary engineering.
We had an industrial engineer try to come in our office, and he's like, "Oh, I'm going to use calculus to improve the workflow here." I was like, I don't know. You can't just string buzzwords together and do nothing. But that's.
All right. So, Andrew, do you have a question for Tim?
I do. So what do you find like your antennas are like used for the most? Like what machinery and like infrastructure, I guess?
Sure. So we're mostly in the, I guess, Internet of Things or IoT field. So it's not like cell phones, but it's pretty much everything else that things need to communicate with. So a couple applications are like we do smart garbage cans and stuff they're like big belly solar. I don't know if you guys have ever seen those, the solar powered trash compactors. But yeah, that's for like basically optimization of garbage routes. For cities so that you don't, waste a bunch of gas, emptying already empty garbage cans. Actually, freaking funny application. I have done, there has been more funny applications. I remember we did one for a company called Stop, which actually stands for Satellite Tracking of People. So it's a kind of a dystopian thing there, but they had an issue where, like people who get DUIs and then they need to blow air into their car to start their car, to take a breathalyzer test. Well, they came to us and we're having this issue where freaking all the drunks were blowing up sober air and then putting it in the back seat and then going into the bar, getting hammered, getting in their car. They grab a balloon out of the back seat, they blow it into their breathalyzer, and it starts their car. So yeah, they needed a smart breathalyzer where they could have temperature sensors and things like this, and then that is connected to the cellular network, and like there's like a live like authorization thing that goes on so that a little more security there. So yeah, they're kind of used in everything. I actually ran into the issue of you'll be walking around and I can't find things that the antennas aren't in. I did the antenna for the Amazon Key for Business antenna, so that gives Amazon the security to every single apartment complex, and so that you can get your Amazon packages. I don't know if the Silicon Valley brainiacs that came up with that really thought about the implications there, but yeah, it was fun. It was fun. I just moved into a new apartment complex, and my antenna was on the freaking keypad to get in. So.
So is it mainly sort of short-term radio wave communications?
Right. I do mostly LTE integration, which stands for long-term employment for me. But yeah, mostly LTE, but I've also done some NFC communications where you're doing like the loop. Basically like almost like a transformer, but it's like, has some sort of read range, the same kind of thing they do for wireless charging of phones and stuff like that.
Right.
Yeah, and then I basically have to do anything below 6 gigahertz. So 2.45 gigahertz Wi-Fi, Bluetooth, GPS, and GNSS, which is a whole nother set of challenges for, accurate satellite communications and, preservation of circular polarization. Satellites are circularly polarized. And then, yeah, all the LTE. So recently, T-Mobile's gone down to 600 megahertz for their 5G things. So I guess I do 5G antennas as well. If we define, I guess 5G is usually defined by whoever's trying to sell you something, or whoever you're talking to. So yeah, I do like the T-Mobile version. I think T-Mobile is using our antennas as part of their testing their phones. So they have like these mini chambers on their desks that they use just for testing like the wireless protocol of their phones. So that's using the PCS 66 antenna, the conical one that I designed. Yeah.
Tanner, do you have a question that you'd like to ask Tim?
Can you hear me?
Yes.
I do have a question.
Okay.
Is there anything that you really wanted to design, but you couldn't really figure it out?
Yeah, I would say yeah, in the early days, it's probably most things. And yeah, not having, I think at my first job, not having any senior engineers above me was a bit of a struggle where I think they just expected me to sit at a desk and develop wonderful products with, fresh out of school with no background. Yeah, but yeah, basically, yeah, you kind of have to take a step back sometimes, and sometimes even just talking about it with someone at your office, and you can come up with some ideas. But yeah, there are times where I get to that complete wall, and then kind of have to take a step back and kind of reevaluating things. But yeah, that happens. It kind of happens to me all the time. You kind of have to sit there and kind of work things through and what's possible and what's not. Yeah, it can be a bit frustrating, particularly when there's not really the resources, or there's not like you're in school. There's always like kind of someone to ask when you get stuck, and then you kind of get to the industry, and you're supposed to be the guy that other people are asking, right? But yeah, there's been tons of times when I get stuck, and then yeah, most of the time I'll just blow up the design and try something else, because I feel like once you've gotten to that point where you're stuck, like your old idea doesn't matter anymore. It doesn't work. So just blow the whole design up and start over. Yeah.
Hudson, do you have a question?
There's this question in the chat about chambers. Is that still?
Yeah, can you hear me?
Yeah, we'll get to that. Go ahead, Hudson, and then I'll look in the chat, Tim.
Sure.
Okay. I was just wondering how you thought like having your background in physics, like if it gave you a leg up or anything rather than just having engineering solely.
Oh, definitely. Yeah, for antennas, for sure. Because there's definitely, I think you have a better understanding of the E&M behind it. Typically, a lot of engineering majors, they'll have an E&M class, but maybe they'll cruise through it, and they're not like, having like an actual E&M discussion in like a small class size where maybe they're in like their big. I remember because I was at RPI and I think I had to take the Fields and Waves class, and I remember being in the class and they say, "Oh, we don't have enough time for antennas. We're going to skip it this semester. Sorry, blah blah blah." And so, oh, what? Well, it's a good thing I already learned it in my physics major, RBSOL. Yeah, no, I think physics is great for building that kind of fundamental and thinking about problems creatively. And like you're saying, like when you get stuck and things and being able to determine the solution, having a physical insight into what's going on, as opposed to just kind of cookie cutter circuit designs. Maybe I know a lot of engineers that it seems like they go to, one application note for one circuit and one application note for another circuit. And they're just kind of like taking pieces of other people's sign and making like a circuit out of it or whatever, and just kind of, here's my power amp circuit, here's this.
Tim, before I go to the question that was in the chat, and it's someone who's actually got a consecutive seminar streak of asking questions, so we have to get to him. I want you to know I recorded this. Is that okay?
Sure. Yeah. Yeah. I don't think anything I've shown or talked about is not.
Well, you can think about it. If I use it for anything, I'll let you know.
It's all completed projects that I talked about.
Okay. All right. So, but anyway, just so you know, I did that, and I can delete it if you want me to. So just let me know.
Yeah, I think it's probably fine. Yeah.
All right. Daniel DeJesus Miniardi asks, I think I missed it, but why are there spike-like walls in the anechoic chambers and not flat walls?
Sure. Oh shoot, I'm not sharing my screen anymore. But yeah, basically the spikes are chosen to be at the lowest operating frequency of the chamber. So the idea is that the spike, you have a spike like this, and then the signal comes in here and then bounces in between these two, and then you need to do that at the higher frequencies to have that kind of to have the signals, be dead by the time they reach. And the idea is that you pick that spike length based on the lowest operating frequency. So for, a chamber that maybe only does higher frequencies, you can have smaller chamber, smaller spikes, etc. But the bigger the chamber is, typically the lower the frequency is. You need bigger spikes to kind of absorb the energy so that you don't, when you get to the wall, there's nothing coming, back off that wall.
So with each reflection, there's also some absorption when it encounters the wall.
Right. Yeah. So it's reflecting in between those spikes there, and then becoming zero power once it reaches the end of the. You need that longer and longer for lower and lower frequencies.
Okay. Daniel's happy with that, and Joseph asks, were you always specifically interested in antennae, or was it something you figured out during your job search?
I think I started playing around with antennas in Fox's circuit class, and then kind of just messing around there. And then, I didn't have, I think I was just looking for jobs that were semi-local and like decent. And I was like, yeah, sure. I kind of fell into it. It wasn't like it was in that movie Contact, where Jodie Foster's a little kid talking about antennas. No, and actually, here's a little antenna tidbit. The correct plural of antennae is antennas. Antennae is only the plural when you're referring to a bug's antennas. There you go. Then you can.
French, did you know that?
No, that's awesome. Thank you.
I'm surprised French didn't know it, but that's good. So Fox got your antenna up so that you were more receptive to the idea.
That's right. Yeah. Yeah. I always. I can't point that out when I'm talking to customers because I don't want to be rude, but I'll be rude for you guys.
Let's see. Gabriel, do you have a question?
I do have a question.
All right.
I was gonna ask Tim, what in the last year or so, what sort of project or sort of thing you were working towards gave you the most trouble, and what was your sort of process for troubleshooting once you got stumped?
Sure. I'd say this array was pretty rough in the past year. That array that I showed earlier with the PCB design. So once you get stumped, honestly, I would say a good suggestion is just to simulate everything, and basically you want to break down any design that you have into its component parts. So you want to break down, when I have this entire thing connected up, right? Let's say there's an issue, it doesn't work, something like that. If I'm hooking up the whole thing, I'm looking at, I'm looking at the low pass filter, I'm looking at the switch, I'm looking at, and then the antenna. So I can't really tell, is it an antenna problem? Is it a, transmission line problem? Is it, is there too much loss through the switch? Is there some sort of thing there? So you want to break the problem into kind of component parts and isolate each part. So here I broke the transmission line. I put a cable going directly to the antenna, put another cable, had a different prototype, put one going to the transmission line, and I was able to determine that it seemed like an antenna problem or some sort of manufacturing issue. Two of the transmission lines had the impedance was slightly not 50 ohms and was providing like a capacitive transformation of the antenna. Too much reactive in the transmission line. So that's why, even though the antennas were identical, I was getting different responses out of the four of them. So I would say breaking everything into component parts and kind of isolating each part, pulling something. Yeah, you definitely want, at some point, want to simplify the problem as much as possible and kind of pull. There's been times where I, do the entire integration and all the different parts and everything. You have heat sinks and everything. And so at one point you do want to pull the antenna out and then say, hey, this antenna by itself, is it a good antenna? Sometimes that's validated because it's an existing part and you already know it's good. but especially when you're doing custom designs, you definitely want to check your ego a little bit there and don't assume that anything's going to work. Transmission line's not going to be 50 ohms just because some calculator on the internet told you it's 50 ohms. Not necessarily anyway, higher frequencies and stuff. And yeah, basically just test everything. When you get stumped there, I think isolating problems is definitely the thing there. And I think and being able to kind of like simulate, I think, things. I know I have some engineers here who are just kind of, oh, this is going to be 50 ohms and that's doing it this. Well, they are until they're not, I guess, and then break it down. I'd say, sorry, it's a bit of a long-winded answer. But.
Any other questions? Yep, go ahead.
Tim, I was wondering if you are happy with where you're at now and if you have any future goals as to where you might want to end up in like the next 5 years.
Sure. Yeah, it's a bit of a deep question. No, I am happy with that around now. I think having this kind of design center, and I was kind of liked it a little bit. It was almost liked it a little bit more when it was during the pandemic. There was no one in the lab, and I could do whatever I wanted all day, and blast heavy metal in the lab and design antennas. Now there's all these people there getting in the way. But yeah, no, it's been pretty good. I was working nights during the pandemic, like something like 11 to 5 or 10 to 5 in the morning. That was good times. No, yeah, I think, I mean, for me, tile glass is pretty. I guess there is kind of like next steps being like, oh, I could work at some fancy company called Amazon or Tesla or whatever. And I just think that kind of live to work kind of lifestyle wouldn't. I mean, a lot more to life than work. So I'm happy kind of where I'm at, and like I don't get a lot of emails and stuff during the day. I'm kind of worked pretty hard to get into happy design land, and not do enough customer facing stuff to keep the lights on, but not like I think if some of those bigger companies, it can be a little bit. I heard a rumor recently that they freaking do like bottom 15% of earners gets fired or something like that every quarter. So I definitely don't want to get into that kind of environment or find out too late that you're in that environment. But on the flip side, I've known people that just work at one of those big companies for 3 years and then you get stock options and then you quit. So it's the other side.
Well, Tim, I think we've taken up a ton of your time. I really appreciate you stopping by.
Sure.
Because I think in particular there are a handful of Engineering 110 students here, so they're a while out. I'm thrilled that Muhammad came by because I was supposed to put you guys together back in July, but my summer didn't go the way I wanted it to. And thank you. It's fantastic to see what you're doing, and
Sure.
quite frankly, how far you've come.
Hey, thanks. Yeah. Oh, yeah. It's been a long, strange trip. Yeah, but make it there, and I wouldn't have made it all this way if I hadn't had the kickstart that Oneonta gave me. So even though I'm not the top 30 under 30, I'll be the top something and something. I don't know.
Well, maybe they'll do a 40 under. Maybe they'll do a 40 under 40. But I have to go now because I have to buy Fox a copper cutter, and that goes with free software so that he can cut antenna patterns.
Yeah, I was going to ask about that.
Oh yeah. I'll send you a link or something. And then you can just take a look, and I'll even send along a free antenna design free of charge.
That sounds great. That'd be fun to see.
Yeah.
All right.
Thanks, Tim.
Thank you, Tim.
Thanks a
Sure.
lot.
Thanks, Tim. That was great.
Great to see you.
Great to see you too, guys.
Yeah.
We can see you here in Oneonta sometime.
Oh, yeah, that'd be great. Yeah, for sure. I'll let you guys know.
All right.
Yeah.
See you, Tim. Bye.
Hey, have a good one. Best of luck. Thanks.
All right. Thank you, everyone who attended.